The Special Theory of Relativity, STR, proposed by Albert Einstein in 1905, revolutionized our understanding of space, time, and the relationship between them. It is one of the cornerstones of modern physics and has had profound implications for science, technology, and philosophy. STR fundamentally challenged and refined the ideas that had been dominant in classical physics since the time of Isaac Newton, particularly in terms of how motion, time, and space are perceived. The special theory of relativity arose out of Einstein's attempt to resolve inconsistencies in the understanding of how objects move, particularly in relation to light. At the time, the prevailing theory of mechanics, Newtonian mechanics, worked well for everyday situations, but failed when applied to very high speeds, particularly near the speed of light. Einstein's insight was to propose that the laws of physics are the same for all observers who are in uniform motion relative to one another, a principle known as the principle of relativity. The special theory of relativity is built on two fundamental postulates. The principle of relativity states that the laws of physics are the same in all inertial reference frames, meaning that no inertial observer can detect their motion through space just by observing the laws of physics. There is no preferred frame of reference. For instance, whether you are sitting still in a room or moving in a car at a constant speed, the laws of physics will apply in the same way. The second postulate, the constancy of the speed of light, asserts that the speed of light in a vacuum is constant and independent of the motion of the source or observer. This was a radical departure from previous ideas. In Newtonian mechanics, speeds were considered relative, meaning that the speed of one object could depend on the motion of another. However, experiments showed that the speed of light in a vacuum is always 299,792 kilometers per second, regardless of the motion of the light source or the observer. These two postulates formed the foundation of STR and led to a number of revolutionary conclusions, which were in stark contrast to the classical Newtonian view of space and time. One of the most important consequences of STR is the unification of space and time into a four-dimensional continuum known as space-time. In classical mechanics, space and time were treated as separate entities. Time was seen as a universal constant that flowed at the same rate for all observers, while space was simply a three-dimensional arena in which objects existed. However, according to special relativity, time and space are interwoven. Instead of thinking of time as an independent dimension, Einstein showed that time is relative to the observer and can be affected by motion and gravity. The concept of space-time combines the three spatial dimensions with time as the fourth dimension, creating a unified model in which the position of an object is described by four coordinates, three spatial and one temporal. In this framework, events that occur in space and time are represented as points in four-dimensional space-time, and the separation between these events is described by the space-time interval, which is invariant. The space-time interval is a measure of the distance between two events in space-time and is calculated using a metric called the Minkowski metric. This interval is the same for all observers, regardless of their relative motion. One of the most striking and counterintuitive consequences of STR is time dilation. According to STR, time is not absolute, but is relative to the motion of the observer. As an object approaches the speed of light relative to an observer, time for the object slows down as measured by the observer. This effect, known as time dilation, becomes more pronounced the faster an object moves. For example, if you were traveling in a spaceship near the speed of light, you would experience time at a much slower rate than someone on Earth. This means that you would age more slowly compared to someone who remained stationary. This effect has been confirmed experimentally in various ways, such as by observing the behavior of particles moving at relativistic speeds and using highly accurate atomic clocks placed on airplanes. Another consequence of special relativity is length contraction, which states that the length of an object moving at relativistic speeds will appear contracted along the direction of motion to an observer at rest. The faster the object moves, the shorter it appears in the direction of motion. This contraction is not noticeable for objects moving at everyday speeds but becomes significant as objects approach the speed of light. As with time dilation, the contraction is only noticeable at relativistic speeds, and it has been experimentally verified in many contexts, such as measurements of moving particles or particles traveling in particle accelerators. Another mind-boggling aspect of STR is the relativity of simultaneity, which states that whether two events occur at the same time depends on the observer's reference frame. In other words, two events that are simultaneous for one observer may not be simultaneous for another observer moving at a different velocity. This challenges our intuitive sense of absolute time and highlights the interconnected nature of space and time. For example, imagine two lightning strikes hitting opposite ends of a moving train. To an observer at rest on the platform, the lightning strikes may appear to occur simultaneously. However, to an observer aboard the train, due to their motion, the strikes may appear to happen at different times. This phenomenon is a direct consequence of the fact that the speed of light is constant for all observers, regardless of their motion. One of the most famous outcomes of special relativity is the equation, which expresses the equivalence of energy and mass. According to this equation, mass and energy are two forms of the same thing and can be converted into each other. A small amount of mass can be converted into a large amount of energy because the speed of light squared is an extraordinarily large number. This equivalence has profound implications, particularly in nuclear reactions. For example, in the sun's core, hydrogen atoms are fused to form helium, and in the process, a tiny amount of mass is converted into a huge amount of energy in the form of light and heat. Similarly, nuclear power plants and atomic bombs exploit this principle to release energy. The special theory of relativity has had profound implications for our understanding of the universe. It has led to the development of general relativity, which extends these ideas to include gravity, and has influenced fields ranging from cosmology to quantum mechanics. In everyday life, special relativity may not seem to have much impact, but it plays a crucial role in modern technology. For example, the global positioning system relies on precise time measurements, and the effects of time dilation must be accounted for to ensure accurate positioning data. The special theory of relativity has reshaped our understanding of space, time, and motion. It has revealed that space and time are not absolute but relative to the observer, and that the speed of light is a universal constant. The concepts of time dilation, length contraction, and the relativity of simultaneity have fundamentally altered our perception of the physical world. Special relativity has not only stood the test of time experimentally, but also paved the way for further developments in theoretical physics, leading to our modern understanding of the universe. Although it defies many of our intuitive beliefs, special relativity has become a cornerstone of modern physics, and its consequences continue to influence both theoretical research and practical applications today.